Okay, so section 2.4, complex loci. So this is the idea of using complex numbers to show a locus of points on an Argand diagram. So let's just start with the main ones that you need to know. So here is this idea of modulus of the difference of two complex numbers. If you think about those two complex numbers as vectors, that clearly you could tell that this is the vector that you are obtaining by from z1 to z2. This here represents the distance between 2 points, how far apart they are, z2 to z1. So if you imagine drawing two vectors, let's say here is z1 and here is z2. So z2 take away z1 is simply you want to get to z2, end of z2, but starting from z1, end of z1. There you go. So z2 take away z1, so you go from z2 minus z1. If you were to draw this on top of that, so move this vector over here, so this is minus z1, you would get that vector which is parallel to that vector, and vectors that are parallel to each other in the same length and going the same direction, they are equal. So this is going to be z2 minus z1. So the way I remember that, it's the end minus beginning. You're only interested in the journey that it takes you from the end of z1 to the end of z2. So if you take the modulus, that gives you the distance between z2 and z1, points of that z2, z1. So the second idea is simply z minus a complex number, modulus of that. So this is the distance between a point, complex number, so a point on an Argand diagram, from another point, which is a fixed point, and that's always constant. This is going to be a circle. Let me just draw that point. So somewhere, I'm not going to draw the axes. So here is AB, which is just to represent the point A plus IB, complex number A plus IB. And here is a point that could be any point Z. And this is that distance R. But that point can be here, could be here, could be here. So it could be a circle. There you go. Okay. So the distance between any point on that circle and this point is always fixed at R. Circle centered at AB, radius R. Okay, the next one is z minus z1 is equal to z minus z2. So z is just general point, all the points. The distance of those points to a point z1 needs to be the same as the distance of the same point to another point z2. So it's equidistant. So we are talking about, let me just draw it and it will become clear. There's my point z1 somewhere on an Argand diagram. There is my point z2. So I need to find somewhere there, fix that point z, one of those. So here is my point z. The reason I've put it here because I want to think about the distance from that point to Z1 and to Z2 being the same. But it could be also over here. The distance from that point Z from Z1 and then to Z2 needs to be the same. So eventually, if you were to map loads of those points, you would see that this is going to be a perpendicular bisector. So this is a line which is a perpendicular bisector of the line segment from Z1 to Z2. This here is actually an equation of that line in a loci sort of way, complex plane way. So is this. This is like an equation of that, again using complex numbers. Okay, so let's have a look at some questions and then see whether we can see what's going on there. So the first one here is Z minus 4. The distance between point Z to point 4 with 0 needs to be 5. So you're talking about the circle. Center of that circle is a complex number 4. So complex number 4 is over here. It's actually 4 plus 0i. We'll write it as a point. And it's always fixed at 5. So the radius is 5. Center 4, 0. We're going to sketch that point, that circle. It's pretty bad drawing, but that will do. Okay, for part B, we need to think about our circle, exactly the same as in part A. And we're going to find, so this means and this line. Okay, so this is, should be so, bracket should be closed here. Imaginary part of all the complex numbers will be equal to 0. So when do we have all the numbers with imaginary part equal to 0? Well, these numbers are on the real axis. The equation of that axis is y equals 0. So we're talking about these are all the points on the imaginary axis. So we are trying to find out the common ground. So what do these points on the real axis and on the circle have in common? They have in common those 2 points. So since this is 5 away from 4, so it's going to be 9, 0 and minus 1, 0. So z is equal to 9, or z is equal to minus 1. That's the complex numbers that satisfy this equation. Okay, so we'll have a look at the second part C. Now we've got again the same circle over here, but this time we want to have a line or the set of all the points Z that have the real part equal to 0. So there is no real part. So we're talking about our y-axis. So this here is y-axis or imaginary axis. So that means the equation is x equals 0. Okay, they only will have I bits. So we're talking about these 2 points. Okay, so let's find out what those points are. We need to get the equation of the circle, Cartesian equation of the circle, and put x equals 0. That's one way of doing it, why not? So the equation of the circle is going to be, if you've got z minus 4 is equal to 5, let me just do it in black. Actually, let's get another piece of paper so you can see it better. Okay, so the equation of the circle that has loci or complex equation like this, you can replace x z with x plus I y if you wanted to, and then you've got x plus I y minus 4 is equal to 5, and then you could see that the real part of this complex number, because it represents a complex number, is x minus 4, and then imaginary part is I y. And then the idea is to get rid of this modulus. Modulus simply means the distance. So this is as if you had a complex number that's real part is x minus 4 and then imaginary part is y. So modulus of that is simply x minus 4 squared plus y squared square rooted. So that's what we're going to write down here. There we go. And you can square it. And if I square it, I should get the equation of our circle straight away. So if you forgot that this represents a circle, you can always get the Cartesian equation by replacing with x plus I y, the z with x plus I y, gathering the real parts and imaginary parts, and imagining, well, you know, just working out the modulus of this complex number. So if my x in this instance is equal to 0, I will have minus 4 squared, so 16, plus y squared is equal to 25. So y squared is equal to 25 minus 16, which is 9. So y is equal to plus and minus 3. But this would be in the real plane, in the Cartesian plane. We are working in complex plane. So these points will be z is equal to plus and minus 3i. There you go. Okay. Okay, example 12. In this example, we have given that z minus 5 minus 3i, modulus of that is equal to 3. So here's a circle. We have to sketch it. So center of the circle, it's always z minus the complex number. So it's z minus 5 plus 3i. So the complex number is 5 across and 3 up. So it's 5 plus 3i. I'll just mark it as coordinates, which is fine. Okay, the radius, so center 5, 3, radius is 3. So we're going to draw that. If it's 3, it's going to touch the x-axis or the real axis. There you go. Cartesian equation, so straight away you can get the equation, but I think if you've got that center, you've got x minus 5 squared add y minus 3 squared is equal to 3 squared, so 9. But it's really good practice to do this from scratch. So if you replace your z with x plus I y, and then you've got minus 5 minus 3i is equal to 3. You can gather the x and minus 5 as your real part of this complex number, and then you've got y minus 3 as the imaginary part. Now if you work out this modulus, it's the real part squared plus the imaginary part squared, square rooted is equal to 3. So if I square it straight away, that will be equal to 9, which gets me to the same equation. Now for part C, they ask us to find the maximum value of argz in the interval between minus pi and pi. So of argz between minus pi and pi, so let's see what they are talking about. So let's go back to the idea, what is the argument? So my z numbers are all the numbers on the circumference of that circle. That's what they are, because these are the only numbers that satisfy this equation. Now, if I were to go to any point whatsoever on that circle, for example this one here, the argument would be that angle that the real axis makes with the line that joins the origin and the point. So really I'm looking for maximizing this angle. So if I travel along the circle, there you go, it will be somewhere here. If I draw a tangent, there you go, that will be the widest angle that I will get. So I need to find out what this angle is. Okay, so how can I do it? Well, if you think about it, by using circle theorems, there's always two tangents that can be drawn to any circle from any point. So here we've got our one tangent that I've already drawn, and the other tangent that's exactly the same in length is going to be your real axis. Now if I draw a nice right angle taking me to the center of the circle, the property is that it's actually going to be another one like this, because the radius are the same both sides, the tangents are equal, so these triangles are exactly the same. So if I can find this angle, let's call it alpha, then our max arc is going to be 2 of these. So what is this angle? Well, this is 3 up, 5 across, so I've got to do arc tan 3/5. So let's do the tan inverse 3 divided by 5 is 0.540 radians. If I double it, I'll get 1.0808. So our angle here is going to be 1.08 radians to 3 significant figures. Okay, let's go to Okay, let's go through example 13. So here we've got a locus, which is a circle centered 12, 5, radius 3. So I've drawn it nicely here. So this point here is 12, 5. And we have to find the minimum and maximum modulus of z. So the minimum maximum distance, minimum maximum value of modulus of z. So we are looking for the closest point to the origin on the circle and the point that's furthest away. So visually you can see that the point that's closest to the center is going to be this one here, which is on the line joining the origin to the center. So we'll find the coordinates of that point in a minute, and then the furthest one away is going to be right on the other side of the circle. Okay, so radius is 3, so this is 3 and this is 3. Sorry, I've already marked it with the coordinates. So if we can find the length of that line, so concentrate on that right angle triangle, which is 12 across, because that's x coordinate of the center, 5 up. Then the line from the origin, let's say this is point P, the center, that is going to be 12 squared add 5 squared square rooted. So that's going to be, it's a Pythagorean triple, that's 13. So the rest is really easy. So the shortest distance here, let's call that point x, and that's y. So min is going to be the length of the line OX. This is simply the distance from the origin to the point P and minus radius. So it's 13 minus 3, which is 10. And the modulus at its maximum is going to be OY, which is your distance to the center plus radius. So we need to go to P and then another 3 units. So that's going to be 13 add 3, which is 16. Perfect. Okay, final example, example 14. I think it's the final one. No, there's 2 more. Okay, so example 14. Okay, so in part A here is the locus. This is a perpendicular bisector between the points with the coordinates 3, 0, and here 0, minus I. Okay, so let's sketch the locus. So this is 3, 0 and minus I. So perpendicular bisector, so it's going to be this line here. There you go. Okay, so that is our perpendicular bisector. Now for part B, we've been asked to find the equation of that line. Okay, so one way of doing it is by substituting x plus iy into this equation. So we'll have a go at doing this. So this is still part A. The first method 1, let's x plus iy replace z in the equation. So x plus iy minus 3 is going to be equal to x plus I, y plus I. So we're going to collect the real part together, then imaginary part, and then x plus imaginary parts here, we'll have y plus 1 on the right hand side. Okay, so the modulus of that complex number is simply square root of the real part and the imaginary part added together, Pythagoras theorem, and x squared plus y plus 1 squared get on the other side. You can actually omit going with square roots, because you know if you square it you get this straight away. So you could have just squared it straight away. Now we're just going to expand this. X squared minus 6x plus 9 plus y squared. And here I've got x squared plus y squared plus 2y plus 1. And you've got x on this side, x on that side, cancel. And you're left with 2y plus 6x minus 8 is equal to 0, which is y plus 3x minus 4 is equal to 0. Okay. The alternative way, method 2, would be simply by using the equation, standard equation of the line. So working out the gradient of the dotted line. So the gradient between I and I 0, 3, 0 is going to be 1/3, because for 1 up you go 3 across. So perpendicular gradient is going to be minus 3. The center of the line joining minus I with 3, 0 is 1.5 and minus a half. So the point is 3/2 minus a half rather than 1.5, and then you do y minus the y coordinate, which is a half, is equal to minus 3x minus 3/2, and then you can just see whether we get the same answer. So multiply that by minus 3, you get plus 9/2. So y is equal to minus 3x minus 3x plus 9/2 minus a half, and this is going to be 8/2, which is 4. So you get the same equation. So you've got two ways of getting this equation. Now for part B, we need to find the least possible value of modulus z. So we are talking about the smallest possible value of modulus of z. So you need to find the shortest distance to the origin. So for part B, we're looking for the shortest distance to the origin. So while I've got it drawn here, let's just visually show what we're talking about. So looking at the coordinates of a point on the pink line, that if you were to go to the origin and you always have the shortest distance, always make the right angle here. You need to make the right angle from the line. So we're looking at the coordinates of that point. Okay, so let's actually get it. Okay, so we are looking for the point of intersection between this line here, which is parallel to that line and goes through the origin. So that line is y equals to, the gradient of this line was 1/3. So it's 1/3 and of x. And the with this line here, which is the y equals minus 3x plus 4. So y is equal to 1/3 of x, and y equals to minus 3x plus 4. We're going to solve the equations simultaneously. So this is going to be 10/3 of x is equal to 4. So x is equal to 4 times 3/10, which is 6/5, or 1.2. The y coordinate is going to be 1/3 times 6/5, which is 2/5, or 0.4. There you go. So final step is to, I think it asked me for the modulus of z at its minimum. So we need to just find that distance. If this is 1.2 or 6/5, this is 2 and 2/5 up. It's going to be 6/5 squared add 2/5 squared square rooted, which gives me 36 plus 4, so it's 40/25. So it's going to be 2/5 root 10. Good. Before we move on to example 15, we have to go through another equation. It's actually a half line. We've already met an equation of a half line, but this time this is argument of z minus z1, so it's actually been shifted to a point z1, and we are going to talk about all the points with an argument of theta from that point. So the argument theta is measured from the positive parallel x-axis drawn from that point going so right horizontally. So we're talking about this actual line, not including the actual point Z1. So all the other points that are making that angle theta from this particular point. Okay, so you need to be able to find the equation of that line. Obviously, you will have to restrict the domain to define this line as a half line subsequently. So to find one way of doing to find the equation of that line is just by using the definition of an argument. So we've got argument of z minus z1. That can be written as argument, remember z is x plus iy, so x plus iy, and let's say minus z1 is x1 plus iy1. So this argument is actually equal to theta, but let's just see what it looks like. So we're talking about argument of the following complex number. If you put together the real parts, it will become z minus z1, and the imaginary part are y minus y1. So argument is, remember, tan inverse of the opposite over adjacent. Opposite is the imaginary part and adjacent will be the real part. So it's going to be arctan of y minus y1 over x minus x1. So if you rewrite the following, theta equals to arctan y minus y1 over x minus x1, then if you put the tan with theta on this side, that will give you y minus y1 x minus x1. So this is already an equation of a straight line, but let's just multiply through and you have tan theta, which represents the gradient, x minus x1. So that's a very good technique of finding an equation, Cartesian equation of the line. Alternatively, all you need to do is find the gradient in a different way, and then using that point find the equation of the line. But this is defined for x's greater than x1. Okay, example 15. Here we've got argument of z plus 3 plus 2i equals 3 pi over 4. So let's just sketch it so we know exactly what's going on. Sometimes when you sketch it and when the argument is so nice and easy, because that's going to be 135 degrees drawn from the point. This is, remember, needs to be z minus. So this is z minus 3 minus 2i. So our z1, the point of attachment of where the half line will begin at, is going to be minus 3 minus 2. So it's minus 2i and minus 3. So we're talking about a half line going at this angle here needs to be 3 pi over 4. Okay, so I actually can work out the equation of that line in an easier way than suggested, but I'll do it in two different ways. So an easier way, because it's such a nice line, is just by looking that this line goes through the point with the coordinates minus 3, minus 2, and the gradient is negative 1. You could see it for 1 across, you go 1 down. So it's y plus 2 is equal to minus x plus 3. So it's y is minus x minus 5. But if you wanted to do it the other way, so method 2, would be by doing the the way I've shown you before. So you've got to have x, y minus the y coordinate, so it's going to be plus 2 over x minus the x coordinate, so plus 3. That gives me the gradient, which is tan 3 pi over 4. So it's y plus 2 over x plus 3 is equal to minus 1, and we get the equation of the line exactly the same as before. So you can rearrange it to give us minus x minus 5. However, this gives you the whole line, so we need to restrict the domain. So x is less than minus 3. That gives me the restriction on the domain. So in part B, that was part B, to find the Cartesian equation. Part C, find the complex number z that satisfies z plus 3 plus 2y is equal, modulus of that is equal to 10, and also on that line. So the other equation is z plus 3 plus 2y equals to 10. So this is circle, centered minus 3 minus 2, radius 10. So minus 3 minus 2, and then radius 10, so we're talking about quite a big circle. Just draw it. So part of the circle, we're talking about finding the point of intersection. So all I need to do is write it as an equation of a circle. So it's x plus 3 squared plus y plus 2 squared is equal to 100, and the line is y is equal to minus x minus 5. I should be able to find 2 points, one here, one over here, but this is not our half line, so I'll be just looking the one that has x coordinate less than minus 3. So let's sub, instead of, I'll expand it straight away. Instead of y plus 2, we are going to have minus x minus 5 plus 2 squared. Let's just expand this, so it's going to be minus x minus 3 squared, which is x squared plus 6x plus 9, exactly the same as before. So you've got x squared plus 6x plus 9 plus x squared plus 6x plus 9 is equal to 100. Okay, so that gives me x squared plus 6x plus 9 is equal to 50. So x squared plus 6x minus 41 is equal to 0. Okay, so let's solve this equation. Okay, whichever way you prefer, I'll complete the square. Okay, so there's two numbers, one is with a plus and one with a minus. Since we're looking for the one that's less than minus 3, x must be equal to minus 3 minus 5 root 2. Let's find the corresponding y value. So this is the real value, the y value. It's y minus x minus 5. So it's going to be minus that, minus 3 minus 5 root 2 minus 5. So it's minus 3 minus 3 is plus 3, and plus 5 minus 5, giving us minus 2 plus 5 root 2. Okay, so my final result is point Z, let's call it Z1, and the real part is going to be minus 3 minus 5 root 2, and the imaginary part is minus 2 plus 5 root 2. Okay, so I believe this must be the last example. You are ready to go and have a go at exercise 2E.